India is preparing for stealth aircraft, long-range missiles, electronic attack and drone formations. Yet the largest combat type in its fighter fleet was designed before any of those threats matured. The Su-30MKI is powerful, fast and able to carry heavy weapons, but its value in a future battle will depend less on raw maneuverability than on what it can detect, understand and share. India has contracted 12 new aircraft and hundreds of replacement engines. A much deeper modernization, widely called Super Sukhoi, is also being designed. The ambition is striking. Retain the Russian-derived airframe, replace much of its electronic brain, integrate Indian weapons, and keep the fleet useful into a far more digital age. This film asks what is confirmed, what is reported, and what such a transformation must actually prove. The letters M, K, and I matter. The Indian Su-30 is not simply a Russian fighter wearing Indian markings. Its development combined a Sukhoi airframe and Saturn engines with Indian requirements and a multinational set of subsystems. Hindustan Aeronautics Limited built the aircraft under license, developed manufacturing and overhaul capacity, and adapted the platform across decades. That history created a large twin-engine fighter with 2 crew members, long endurance, thrust vectoring control, and the volume to carry substantial sensors and weapons. It also created a dependency puzzle. Some parts are Indian, some are Russian origin, and earlier avionics came from several foreign suppliers. Super Sukhoi is therefore not one clean replacement. It is an attempt to change the integration authority, the ability to connect sensors, computers, electronic warfare, and weapons without waiting for every original vendor. The timing is driven by arithmetic. New fighter programs take years to design, test, and manufacture, while aircraft already in squadrons must remain available every day. In December 2024, the Ministry of Defense signed a contract with HAL for 12 additional Su-30MKI at an approximate cost of 13,500 crore rupees. The government stated an indigenous content of 62.6%. It also approved 240 AL-31FP engines for fleet sustainment, with delivery spread across 8 years. In a May 2026 investor call, HAL said the new aircraft were scheduled for delivery late in the decade and described the upgrade as being in its design program. Together, those decisions show commitment to the platform. They do not prove that the full Super Sukhoi configuration is already approved, tested, or ready for squadron service. At the center of the reported upgrade is the radar. The existing BARS system is a passive electronically scanned array. It can steer its beam rapidly without rotating the whole antenna, but energy is generated centrally and distributed across the array. An active electronically scanned array divides transmission and reception across many solid-state modules. Software can shape and reposition beams extremely quickly, revisit targets at different rates, map the ground, and support electronic protection. Failure can also become gradual. Losing individual modules need not mean losing the entire radar. But AESA is not a magic range multiplier. Performance depends on aperture, transmitted power, receiver sensitivity, cooling, waveform design, processing, and the target itself. A large fighter nose creates opportunity. Turning that space into reliable detection and tracking is a system engineering problem, not a module count contest. Indian reporting calls the new radar Virupaksha and describes it as a large indigenous AESA related to the UTM family. Recent coverage says a private industrial partner is building the active antenna array unit, while DRDO leads development. The same reporting attaches impressive module counts and detection ranges. Those numbers should be treated cautiously. Radar range changes with target radar cross-section, aspect, altitude, clutter, waveform, and the probability of detection demanded by the operator. Publicly available official material does not provide a certified Virupaksha performance sheet. The meaningful milestone will not be a claimed maximum distance. It will be stable power-on tests, airborne trials, tracking against representative targets, resistance to jamming, integration with the mission computer, and reliable production hardware that can be installed repeatedly across operational aircraft. A modern fighter must also understand who is illuminating it. In March 2023, the Ministry of Defense contracted Burrid Electronics for 129 Dr. 118 radar warning receivers. The government explicitly said the equipment would enhance the electronic warfare capability of Su-30MKI aircraft, and that most subassemblies would come from Indian manufacturers. A radar warning receiver does not make an aircraft invisible. It detects and classifies radio frequency energy, helps identify threat emitters, and supports decisions about maneuver, jamming, and countermeasures. Its effectiveness depends on antenna coverage, sensitivity, signal libraries, and how quickly ambiguous emissions can be turned into useful warnings. When fused with the fighter's own radar and other sensors, electronic support can change the crew's picture from isolated alerts into a coherent map of the electromagnetic battle. That fusion is where the upgrade becomes more than new boxes. Every new sensor creates data. The mission computer must decide what that data means, correlate tracks, remove duplicates, prioritize threats, and present a usable picture to two people moving at hundreds of meters per second. That demands processing power, but the harder challenge is architecture. Interfaces must carry radar plots, weapon status, navigation, electronic warfare warnings, and information from other aircraft without introducing dangerous delays or conflicting identities. Open interfaces can make future weapons easier to integrate, but only if timing, cybersecurity, and flight safety requirements are controlled. Displays must change as well. A pilot cannot exploit sensor fusion through a cockpit designed around separate instruments. Super Sukhoi will succeed only if the software and human-machine interface turn many upgraded subsystems into one aircraft. A collection of advanced components that cannot exchange trusted data is still an old fighter with expensive attachments. The Su-30MKI size becomes an advantage when the mission is to carry large or numerous weapons. BrahMos has already been launched from the aircraft, proving that an unusually heavy supersonic cruise missile can be integrated with the platform. The Defense Acquisition Council has also approved an indigenous long-range standoff weapon for integration on the Su-30MKI. Astra gives the aircraft an Indian beyond visual range air-to-air path, while future variants could demand better radar tracks and longer mid-course support. This changes how the fighter should be judged. It may not need to penetrate deepest by itself. It can act as a high-capacity launch platform receiving targeting information from other sensors, but range brochures are not kill chains. A weapon still needs identification, track quality, communications, rules of engagement, and terminal guidance. The aircraft's new brain matters because it connects those steps. The engine story requires a careful distinction. In September 2024, the Cabinet Committee on Security approved procurement of 240 AL-31FP engines from HAL for more than 26,000 crore rupees. The government described them as a fleet sustainment requirement and said indigenous content would exceed 54%. That is strategically important. Engines are consumable life cycle assets, not permanent parts that remain untouched for decades. Manufacturing and overhaul capacity determine how many aircraft can actually fly. But replacement AL-31FPs do not automatically create a higher thrust Super Sukhoi. Public confirmation of an entirely new propulsion system is absent from the material reviewed here. The upgrade must therefore manage the electrical power and cooling demands of new radar and avionics within a realistic aircraft configuration. More capable electronics are useful only if the jet can power, cool, and maintain them on the flight line. Modernization sounds modular on a presentation slide. Remove the old radar, install the new one, connect weapons, update software. Aircraft do not behave that way. A heavier antenna changes structural loads and balance. New electronics add heat. Cooling pumps consume power. Power converters create electromagnetic noise. Cables, computers, and displays must survive vibration, temperature, and high-G maneuvers. Each weapon needs separation trials, software validation, and firing clearances. Then every modified aircraft must match the approved configuration closely enough to maintain and troubleshoot. This is the integration tax. It explains why a design program can precede operational conversion by years. HAL's manufacturing knowledge and DRDO's sensor work provide a foundation, but the real measure will be repeatability, not whether one prototype flies, but whether dozens of aircraft can be upgraded, tested, and returned to squadrons at a useful rate. Powerful radar does not turn the Su-30MKI into a stealth fighter, and it does not guarantee effortless detection of one. The aircraft retains a large conventional airframe, external stores, and exposed engine faces. Those features can produce substantial radar returns. Against low observable targets, the upgraded crew may benefit from better processing, networking, and electronic support, but detection is a contest of geometry, frequency, power, target aspect, and tactics. A stealth aircraft is not invisible. Its design reduces detection and tracking opportunities in selected bands and directions. Conversely, a non-stealth fighter can remain valuable by standing farther back, carrying long-range weapons and sharing data with other sensors. The honest Super Sukhoi argument is therefore not that electronics erase the airframe's signature. It is that better information may allow the aircraft to use its payload and endurance without pretending it has become something it is not. The evidence supports a clear baseline. India has ordered 12 more Su-30MKI, committed to hundreds of engines, contracted indigenous radar warning receivers, and approved new standoff weapon integration. It also has an upgrade design effort surrounded by reporting about Virupaksha, new computers, and a much broader Indian electronic architecture. The gap between those two layers is the story. Super Sukhoi must still demonstrate an airborne AESA, fused sensors, electromagnetic compatibility, weapon clearances, maintainability, and a conversion rate that matters before the fleet ages further. If those gates are passed, India will not have created a stealth fighter from a flanker. It will have done something more practical, taken control of the mission system inside its largest fighter fleet. The future of the Su-30MKI will be decided not by how dramatically it turns, but by how intelligently it connects.